Hello, good morning, good afternoon, good evening. Welcome to eCHO. This is eCHO 179, quite a lot of them now. And this week we are going to be talking about transparent proxies, what they actually are when compared to other type of proxies, some examples of these proxies that you may have come across whilst implementing solutions and things like that. And then we'll look at a bit of eBPF code, which would allow us to effectively implement the same sort of functionality that you would kind of get from doing things with, say, IP tables. So before we kind of kick things off, good afternoon to Tony. Hope you're well. So I'm just going to get my show notes up and we'll kick things off. So, as I mentioned, it's episode, let me just pop this down. This is episode 179, transparent proxies. So, before we kind of kick things off, let's talk about kind of what's up and coming that may be of some interest. So, this week was the AWS Partner Summit. The Linux Foundation, or the CNCF, announced Open Observability Con and OTel Community Day. So this is a whole new, I guess, conference, which is all focused on observability and things like OpenTelemetry. As ever, KubeCon is there in the background waiting for us. So the CFP has been open for a couple of weeks for KubeCon North America, which is going to be in Atlanta in, I think it's October or November. And then there are a couple of other events. So there's Open Source Summit Korea, which is also in November. The CFP is open. You have 2 more months to get a talk submitted. Open Source Summit Japan, that's in December. And then Open Compliance Summit also in Japan. So a lot of events. They never end. And then in terms of news, obviously there is the Cilium newsletter, and then I've attached here another article which I came across, which is a blog post by someone who has a home lab, a very crazy home lab, and they were effectively wanting to do the best amount of IOPS from basically this one server filled with SSDs and things like that. This individual ended up writing a bunch of really kind of quite interesting eBPF code in order to fully understand everything that was kind of happening and improve the performance on this crazy AMD home lab box that he had, which 384 CPUs and getting huge amounts of IOPS from what was in there. So I've attached that. Couple more hellos. So hey Joseph, hope you are well. And hello Ganitak, hope you are well as well. Just to say, as we're stepping through all of this, if you have any questions, my text is too small and you can't read it, or I have explained something poorly and you want me to go into more detail or anything like that, please do let me know. And as soon as I spot your comment, I will do what I can in order to answer that. So transparent proxies, that's the topic of today. So transparent proxies aren't a new thing. They have existed in various guises for quite a long time. I suppose before we talk about transparent proxies, we should actually talk about what a proxy is anyway, and what the difference is between a proxy and a transparent proxy. So effectively, a proxy is something that sits in between, and proxies your connection or your data between you and somewhere else. You may have come across things like SOX proxies or SOX proxies are pretty much an easy way of kind of redirecting traffic through somewhere else. So it's kind of quite easy with SSH, for instance, to SSH somewhere and set up a SOX proxy, and then you can effectively set your system to use that proxy and send all data back and forth between it. So, for example, you wanted to watch some video that was in another country, you could SSH to a machine that was in that other country, enable the SOX proxy, configure your system to send traffic through there. Now, whenever you're trying to access whatever it is that you're accessing, you look like you're coming from where that proxy is located. I don't condone doing whatever it is you need to do to do these sorts of things, but I mean, that is effectively what a proxy does. That is a proxy that you need to configure your system to go and interact with. But today we're talking about a transparent proxy. And what that means is that the act of proxying is completely transparent to either the end user or to the application itself. So we don't need to configure any changes. We don't need to rewrite the code or even actually know about that proxy. And there are a lot of places in enterprise environments and things like that where transparent proxies sit in a variety of different areas, largely to ensure security or observability or things like that. So this is the why of a transparent proxy. So as I mentioned, and I spelt it wrong, observability. So effectively sitting in the middle and being able to watch that traffic as it goes around and, kind of use that to actually understand or generate statistics based upon where the traffic is going, where it's originating from, and things like that. Security. So there are a lot of transparent proxies that will do things like TLS or TLS termination, things like that. So effectively, an end user is sending unencrypted data to something. The transparent proxy will effectively do the TLS on top of all of that, and it will handle the connection between itself and wherever it is that you're trying to access. Additionally, because we sit in the middle, security around things like blocking traffic or content filtering. So as you are, to the end user, they're just accessing the internet directly, but this proxy is sat in the middle. It can effectively say, this website is not allowed and things like that. So if you're in a corporate environment and you try and access something you potentially shouldn't be doing, a transparent proxy is more than likely going to be sat in the way and will report you to your manager that you've been looking at the wrong things on the internet. Application use cases, so redirecting traffic. And then finally, caching. So being able to know what it is that you're trying to access. So effectively, if you're going to various websites and things like that, and you're continuously kind of pulling the same image, instead of you having to continuously pull that same image all the time, you could have a transparent proxy which keeps a local copy of some of those assets. So instead of you having to, as I say, waste bandwidth, you keep a local copy of that. So some examples of these transparent proxies. So Squid is effectively, I think, the first transparent proxy that I ever came across. And Squid really was kind of quite important back in the day when internet bandwidth was at a premium and things like that. So, before, I guess, most people had, multi-megabit connections, and they were living on dial-up and things like that, or ISDN or something around those sorts of speeds. Having something that would cache various images and save that small bandwidth became kind of quite important. So Squid proxy sits in the middle. It watches effectively the HTTP gets that you're doing. And it will keep a hot cache of things that are being accessed regularly. Eventually, when things get cold, they'll be removed from local disk until there's enough pulls of that in order for it to keep a warm copy of that locally. So when you need to download it, you get the local copy as opposed to having to go to the internet and, again, waste that valuable bandwidth. Another example is MIT proxy, or man in the middle proxy. And then kind of more modern example is envoy proxy. So everybody's favorite service mesh proxy, which you have on your system either as a sidecar or as a daemon set or whatever, and is configured to do a variety of different things. But how do we get traffic into these proxies? Because as I've mentioned, the route to a proxy in our example is transparent. So as I mentioned, the application doesn't need reconfiguring. The traffic automatically gets to the proxy. So how does that happen? Well, there are a couple of different ways that we can do this. And the most common way is through IP tables. So yeah, I mean, IP tables, if you've not come across IP tables before, welcome to your first echo, because I feel like we talk about it quite a lot. But IP tables is a way of configuring behaviors of IP traffic on a Linux machine. You could do these same sort of behaviors on other systems as well. So if you're running a Mac, for instance, you would do it with PF, which is kind of like the BSD firewall, but it allows you to do the same sort of thing. So steps are pretty straightforward. We would need to enable IP forwarding. We would need to have Squid running. So at this point, we've installed Squid. We've set up the config for it, so we told it where it needs to store its local copies of images and data and things like that. And it's now running on port 3128. So what we've now done is created an IP tables rule. And that IP tables rule is going to do pre-routing. So that's before connections are actually made. This is going to be on the Ethernet interface. We're going to care about TCP only. And the destination port of port 80. So this is not HTTPS, this is just HTTP. But effectively, any connection outbound from the machine that this person is on that is going to port 80 doesn't go to port 80 where it's actually going. It's actually going to be redirected to a different port on the local machine. And that port is going to be port 3128. So what we've actually done is we've kind of tromboned the traffic. So instead of it going out, it's actually looping back and going to port 3128. So we've kind of a loopback connection to our Squid proxy. So the application, as I mentioned, doesn't know. Traffic has just been captured through IP tables and sent to Squid. Squid then will get a connection from the application. It will understand that there's a HTTP request. It will be able to parse that. So it'll basically be able to see /get index.html. It's a quick question here. What is special about the 3128 port? So that is the default port for Squid. So that's why we're redirecting to that default port. You could configure it to be a different port if you wanted to, but if you're deploying Squid, then that's effectively what it's going to be. Other applications that do proxying, like Nginx, maybe sat on 8080 or something or other like that. So this is just 3128 is the Squid one, and we're just using it as an example at the moment. HTTP is fine because it's quite easy to do. For HTTPS, that's where things get a little bit harder. We can do some stuff so we can generate our own certificate for Squid to use. And Squid will use its certificate then to speak to the other servers. However, your browser will give you an error saying, I'm not speaking to google.com, I'm actually speaking to localhost or something or other like that. So you would actually then need to configure your browser to allow that and things like that. So HTTPS is kind of quite difficult with doing things like proxying in the middle, but not impossible. Pardon me. And then this I thought was kind of quite interesting as I was researching content for today. If you have written your own application and you have built it using curl, or the libcurl, for instance, libcurl by default has proxying built in. So you've done an import curl.h headers and this, that, and the other, and you've compiled it against the libcurl libraries. There are a bunch of environment variables that you can set. And the libcurl portion of things will look for those environment variables and actually proxy things based upon those environment variables. So Squid has built-in proxying that your application doesn't need to know about. So that's it's a bit of a funny one, that one. So we've talked about proxying, why it exists, the kind of types of proxying. So a non-transparent proxy where you know about it and you connect to it and send traffic through it, or a transparent proxy which by its nature is transparent, you can't see it, you don't configure anything to, or the end user or the application isn't configured to send traffic through it. Let's talk a little bit about how we could do the sort of thing with eBPF. So we're going to quickly look at a proof of concept that I put together a while ago. Let me just stop sharing this. So bear with me. Right. Let me bring this in. So that didn't work. Never mind. Many moons ago, I basically put together a quick example of doing the same sort of thing with eBPF. Let me make this a little bit bigger. That's ruined the formatting. Okay, cool. So in the original architecture that we're talking about here, and we're going to be doing this inside a Kubernetes cluster, two pods speaking to one another. Nothing really will sit particularly in the middle of that. The CNI will effectively take care of routing traffic, but it won't do any sort of proxying. It won't care about what's actually happening. Most CNIs, unless you turn these sorts of functionality on, are largely just focused on shuffling packets from source to destination. So what we need to consider is how we proxy in the middle. And with service meshes, so if we wanted to have Istio in here, and I think there's an example of it. Let me see if I can quickly find it. Actually, yes, it's in my notes. I'll just get this open again. So Istio effectively takes care of doing things like putting Envoy pods everywhere for you. And then Envoy understands the traffic and moves it around. There is an example somewhere of the Envoy IP tables. Bear with me a second. Here we go. So here we go. Let's bring this in. So yeah, Istio effectively kind of handles a lot of all this sort of stuff, and it will effectively take care of configuring IP tables rules all over the place in the kind of same way that I mentioned, so that traffic coming in and out of pods is redirected to the Envoy proxy, where the Envoy proxy then will make higher level decisions on where that traffic should go or inject behaviors, potential faux faults or whatever it is in order to simulate various use cases. But if we look here, it's kind of quite intense, I guess, to a certain degree. The amount of things that actually are required to happen within a pod that has its own set of IP tables rules. I suppose one thing to add really is with this sort of architecture, you have many different IP tables rules. You actually have the host IP tables rules. You have each pod in its own net namespace. So each pod can have its own set of IP tables rules that happen within the pod. When traffic then leaves that pod and goes to the host itself, there'll be another set of IP tables rules, and so on and so forth. But we can kind of see in this example with Istio and Envoy, Istio will effectively take care of doing all of the IP tables rules inside of the pod. And in this example, a remote pod is sending traffic to another pod. The IP tables rule will pre-route it, send it to a couple of other chains inside of here. So we go from pre-routing to Istio inbound to Istio indirect. So if you follow the numbers, that's 1 to 2 to 3 to 4. And 4 is where traffic is now redirected to Envoy. Envoy will do its magic. And then let's see where we go from there. From Envoy, we then go to 5, which is output. So Envoy has processed traffic coming from a remote pod. It then goes to Istio output. Yeah, which is number 7. And then post routing, which is traffic leaving IP tables and all the traffic control, is where it then finally goes to the application that's actually running. So it's a lot of things happen getting traffic into a pod through the pod's IP tables rules, into the transparent proxy to be processed by the transparent proxy, then out of the proxy back into IP tables, where it then will finally go to the application itself. So IP tables is incredibly powerful, but you can start to see a little bit where this can become a bit of a large thought process when you are debugging and things like that. So yeah, that's typically how things work today. If you have Envoy and Envoy as a sidecar and things like that. The alternative that is being discussed at the moment is Z-tunnel or Z-tunnel, depending on how you pronounce that. And that effectively is another way of capturing traffic, where traffic, instead of going through a lot of IP tables rules, goes through kind of like a REST tunnel and is sent then to a single Envoy process, as opposed to IP tables capturing everything and doing the local processing inside the pod itself. Right, so back to our example. So instead of having IP tables do all of the things that are actually happening, can we do the same with eBPF? And yes, the answer is yes. So instead of like a myriad of IP tables rules, we can basically hook into the kernel and understand the traffic and add rules in there, which will, instead of allowing pod 1 to speak to, hang on a second. There we go. Instead of pod 1 speaking directly to pod 02, we're going to need to redirect it to our transparent proxy. And we're going to do that with eBPF. So I think right, so this is the diagram. I hope it makes sense. If not, I'll walk you through it anyway. So our pod 01 wants to speak to pod 02. eBPF understands that a connection is going to occur and things like that. It will do a map lookup. And what it's actually going to do is we're going to have a sidecar. I know they're not on vogue at the moment, but we're going to have a sidecar anyway. Our sidecar is going to be sat there listening on this port, which is going to be 1800, which is going to be sat, as I mentioned, as a sidecar inside our pod. And eBPF will rewrite the destination to send that traffic to our local listener. It will also then store the original destination, because we need to know where the traffic is meant to actually go. And then our man-in-the-middle program, our proxy, will basically then be able to do things like TLS encryption between our two sidecars, pop the encryption on the other end, and then send that raw data to our 10.0.2.2. So like we did with IP tables, we're going to use eBPF to see traffic, to understand that traffic, to modify the packets if we want to, so that they're redirected to our proxy instead, and then our proxy can do whatever it needs to do. So I will quickly kind of walk you through the code. We've had this code on before, actually, but I was going to say it's pretty straightforward. It's straightforward enough. Does anybody have any questions that need covering at this point? All right. Good work, everybody, for having no questions at this point. So these are the areas that we're going to hook into in the kernel. So we're going to hook into this connect for call, which is a C group specific call. So whenever the connect for syscall is triggered, and that is when there is a IPv4 connection to a remote address. We will see, we do a few checks on the context of that connection. So we make sure it's TCP only, because we're not going to do UDP in this instance. And then what we will do is we will look up the, we will get a config. So we have a singular config here, which has things like the pod range that we care about and things like that. So this is basically some things that we're passing into the, this is a config that we're passing into the eBPF program itself. I think that is defined in here. Yep. So this is all of the things that it cares about. So this is going to be the local host. This is going to be a port that our internal proxy is going to listen on. And this is important as well. This is going to be the process ID of the proxy. The reason being is we need to know that so that we don't send traffic from the proxy back to itself, because we are going to be capturing all traffic. We will be capturing that traffic and sending anything to the proxy. However, if we see that that proxy, the traffic is coming from the PID of the proxy, then we don't touch it. Otherwise, we will just loop traffic into the proxy and keep sending it to the proxy. So carry on stepping through that. We get the original destination, so where traffic is actually going. Oops, sorry. And let me just check. Yep. We get the mask. So here we get the CIDR of all things that are pods, which we pass in to our running proxy. The reason is that we're only really caring about proxying traffic for pod-to-pod communication. That's because those pods are going to have the sidecars that will do the clever magic. If we are proxying to something outbound, like Google, for instance, then my clever proxy won't be there and the traffic won't make any sense when it gets there. If the packet's not part of the pod CIDR range, then just ignore it and let it carry on about its merry way. Here we capture the port of the remote destination. So we store that in destination port. And then here is where we get our PID. So this is the PID of the running proxy. And we have a particular function here for doing namespaced lookup PIDs. The reason being here is if we use the eBPF function get ns PID, it will give us the PID outside of the pod. So we will get something like 10,000 or whatever, whereas it's actually going to be like PID 2 because there's only going to be 2 processes running inside of the pod. And then finally, some other things just to make life easier. Don't worry about traffic hitting kubelet because that can cause loops. Each connection inside the Linux kernel has a cookie, which is what is the unique identifier for each of those connections. So we get that cookie to ensure that we know that this is a unique connection. And then finally, we get or we configure the other bits that we actually want to do as well. So here is where we change the context to have the destination of our proxy, which is going to be potentially localhost. Here we change the port to be our proxy port. So the traffic effectively has been redirected so that it's now going to go to the proxy that's actually running. And that's it. So we've stored a bunch of information about that connection. It's a new connection. We've stored its cookie for looking up later on. We have looked up our config. So we found our proxy. We found our proxy port, our proxy address. And we have redirected traffic now going, instead of it going to pod 02, it's now going to go to our proxy instead. And then we've got a couple of other functions that we've defined here. So this is interesting because this is a hook into something that we call inside the proxy. And we use this in order to do a lookup to work out where traffic should actually go. And the reason being is when we've redirected traffic to our local host, the proxy will receive it, but the proxy will have no way of knowing where that traffic was originally meant to go. So what we do inside our proxy is we do let me see if I can quickly find it. Bear with me a second. I should have found this earlier, actually. Here we go. Right, I'll talk about this in a second, but this is the function that we need to care about. Oh, yeah, I'll actually talk about it now. Oh, I've lost it. Right, yes. So this function, what we can do is on a socket, when we get a connection, we can get the socket options around that, which will effectively get us a bunch of information about the socket itself. And we use that to actually get everything that we stored previously. So on a new connection, we store the original destination, the original port, and map that to the connection cookie. We can do a syscall now inside our proxy based upon that cookie to get that bit of information that we actually stored. So inside our eBPF program, we will do a lookup based upon the cookie. And what we will get then is we will get the original source port, the original destination, and update the map to get that information, where we can now get that inside of our proxy. So we now know where the original destination is. at which point then our proxy knows to send traffic to the other sidecar, but with a modified port. Our proxy then will decapsulate everything and then send it over to the pod as expected. So we're now doing transparent proxying, and we are now doing proxying as well. So eBPF is modifying the traffic. It is storing the original destination so we know where it needs to go. It sends all that information over to the remote proxy, which is a sidecar in the remote destination, where it does what it needs to do. So, are there any questions? Have I confused anybody? Is there anything that didn't make any sense? I'll give you like a couple of seconds whilst I get some water to see if anybody needs anything covering in a little bit more detail. Okay. I'll take it I've explained that. Okay, so let's quickly walk through that as a demo. Share screen. I'm certainly going to have to make this text a bit bigger, I imagine. So give me a second. And I'm going to have to remove the banner because you won't be able to see that. There we go. Right, I'll make this a bit bigger so you can actually see it. Okay, so I've lost the ability to type. Right, so we can see here we've got a simple kind cluster. There's nothing running on it. What we'll do first is we're going to apply a simple workload. So as we showed earlier in that example, we have two pods that are going to speak to each other. We can see they're up and running. And what we're going to do is we're just going to TCP dump on this so we can see. Right, there we go. We can see here that there is traffic going backwards and forwards. We can see that there's HTTP responses. The HTTP response is okay. That's being sent backwards and forwards. We can see that there is a request. So something has done a get to us. So we've got traffic coming backwards and forwards between the two pods. All is well, but nothing is encrypted. A lot of lessons with how all that works inside the C code for the eBPF. Yes, well, it's not a huge amount of code. It's more the nuances of so like the redirect is pretty straightforward. We're effectively taking the packet and finding the sources and destinations or whatever and just exchanging values. The trickier part comes with passing the other information backwards and forwards. So how do we stash the original destination somewhere? Because we can't add anything more to the packet. The packet is going to be received by the destination, but it'll have no way of knowing that original destination. So we have to come up with ways of, as I mentioned, stashing that information and finding another way to do those lookups. So as I mentioned, we have traffic unencrypted going backwards and forwards. We'll pop out of here. Let's delete our demo. Right, what we're going to apply now is, oops. What we've applied is our controller. So what we need is something to do a few things. I'll quickly show you actually. So we have our sidecar injector. This is going to do a mutating webhook. So whenever pods are created, our proxy and eBPF will be added alongside them. Now, what we're going to need to do is have something in the middle to handle all of the certificate generation. So that's what this is actually going to do. When our pods come up, it will generate certificates for both of them based upon an authority, so that they're allowed to speak to each other and they understand that they have a shared authority. So effectively, they're going to have mutual TLS between the two. So let's now reapply our demo. So what we'll see now is instead of there being just a single container, they've been modified on creation so that they now have two containers running inside them. And what that means is our original workload is going to be running as it was before, but now we have our transparent proxy sat in there. Now we have our proxy sat in there, and now we also have eBPF inside there doing the transparent proxying, so the redirect and things like that. Now, you obviously can see that there's two errors here, and there's a reason for that, and we can see why. So if I quickly get my pods again. So if I look in here, we can see here these two lines, which is where we created the secret. So the reason that the pods took a second to restart is because they were waiting for these secrets to be created. And in these secrets are the keys, not the keys, are the certificates used in order to have encryption between the two proxies. So now, if we go back into our control plane where everything's running, and we look at the Ethernet adapter of one of the two pods that's been created. No more gets. It's all encrypted. So we now can no longer see anything. We can't see what the traffic actually is anymore. It's all been encrypted between the two pods. You can see that the two pods. Oops. I've lost my window. Here we can see the traffic originating from one pod and going to the other and sending back, and all of it is encrypted. We've not added encryption to the application. The application is the same application that it was before. Instead, we are taking their traffic. We're now encrypting it at source and destination, encrypting at source, decrypting at destination, and the same in the opposite direction. So transparently, we now have encryption added to our application. Quick question here. Is it also possible to implement a man-in-the-middle proxy such that traffic can be inspected using TLS on both sides? So yes, with eBPF, and there's a number of examples around this. But for instance, if you can guarantee that the application is using things like libSSL or whatever, you could write code that will hook into the libSSL uprobes, and functions like SSL read and SSL write. Those two functions will effectively show you the data before it is encrypted and the data after it's encrypted. So you'll be able to effectively see the raw data as it's before it actually hits SSL and things like that. You'll be able to pull that information out of the library. Additionally to that, and there's a good example on a project called eCHO, is capturing SSL session keys. So session keys are, so there's a bunch of things that happen when a connection is created, but the session key is the one thing that's required in order to decrypt the data on the other side. If you can get that session key with SSL, then effectively you can replay all of the traffic. You'll need to capture it with like TCP dump and and this, that, the other. You can then replay it with the session key and decrypt all of that information. So yeah. So yeah, transparent proxy with eBPF and a bit of Go code to do the actual proxy in between the two pods. Are there any questions about that? Anything that I didn't explain or could do with more explanation? Cool. Okay. Well, thank you very much, everybody, for joining today. Thank you very much for the good questions. If anybody has any feedback or any particular things that they would like us to cover in upcoming sessions, eCHO sessions about eBPF or Psyllium, Tetragon, Hubble, please do let us know. You can find us on Blue Sky, on Slack, etc. Yeah, thank you very much for joining today. Have a fantastic weekend, and I will see you all next time. Thank you very much. Oh, hang on. Sorry, there is a question. Or a thank you. 1 second. Cool. All right. Thank you, everybody. And I'll speak to you all next time.